Welcome to qnawire.
First, note the diagram of the situation. Initially, we have a satellite that is orbiting the Earth at a radius of RE, small re, from the center. The radius of the Earth is big RE, and the mass of the Earth is ME. The satellite then orbits the Moon. The Moon has mass M subscript m, radius capital RM, and the satellite's orbit from the center of the Moon is little rm. Note that the altitude above the surface of the planet or the moon of the satellite is little r minus big R. So the first thing to note is that the radius of the Earth is equal to 6.37 times 10 to the 6 meters. The radius of the satellite's orbit about the Earth is equal to the radius of the Earth plus the altitude of the satellite's orbit. Since both of these are known, we can calculate this value. So this is 6.37 times 10 to the 6. These are both in meters, plus 4.5 times 10 to the 6. Hence we get little r to be 10.87 times 10 to the 6. So essentially, the satellite is 10.87 times 10 to the 6 meters from the mass center of the Earth. So initially, let's look at part A. In part A, we know that the force between the Earth and the satellite is equal to gmm over r squared, or the force between any two massive objects, one with mass capital M and the other with mass little m. And we know from another equation, equation 29, that capital G times capital M is equal to little g, the gravitational acceleration on the surface of that planet, times the radius of that planet squared. So this implies that the force between the two objects is g r squared m over r squared. And m times g we can simply write as w, the weight of the satellite, over the radius of the planet divided by the radius of the orbit of the satellite, all squared. So great, we can now use this equation to find the force on the satellite in the Earth's orbit. So when it orbits the Earth, the force F is equal to its weight, which is its mass, 500 kg, times g, which is 9.81 meters per square second, times the ratio of the two radii, the radius of the Earth being 6.37 times 10 to the 6 meters over the radius of the orbit, 10.87 times 10 to the 6 meters, and that's squared, all that squared. So we get the force between the Earth and the satellite to be 1,684 newtons. So that's our answer to part A. For part B and the solution to problem 78, we know that the mass of the planet is equal to 1 over the universal gravitational constant g times 2 pi over the period of the satellite tau, all squared, times r cubed, little r cubed. So obviously, if we rearrange this equation, we can find an expression for tau in terms of the other variables. This is 2 pi r to the power 3 over 2 all over the square root of g times m. Now remember, we want the two periods to be the same. So tau e must equal the period of the satellite around the moon, tau m. This implies that 2 pi times the radius of the Earth, the radius of the satellite's orbit about the Earth, to the power 3/2, all over the square root of g times the mass of the Earth must equal to tau m, which is 2 pi, the radius of the satellite's orbit about the center of the moon, to the power 3/2 over the square root of g times the mass of the moon. So what we can see is that from here, the radius of the satellite's orbit about the moon, Rm, is equal to the mass of the moon over the mass of the Earth, mm over me, to the power 1/3 times the radius of the satellite's orbit about Earth, Re. And so this, when we plug in our values, gives us 0.01230 to the power 1/3 times Re, which is 10.87 times 10 to the 6 meters. And so we get the radius of the satellite's orbit around the moon to be 2.509 times 10 to the 6 meters, which is 2,510 kilometers. So the radius of the satellite about the moon, the radius of the satellite's orbit, needs to be 2,510 kilometers from its center. And lastly, we want to calculate the gravitational acceleration at the moon's surface. So we know that gm is equal to gr squared. So if we substitute it into our equation for tau, we get two pi re to the power 3/2. Remember, if we go back to our equation for tau, equation 1, and we substitute in for gm, 2 pi 3/2, 2 pi re to the power 3/2 over the radius of the Earth times the square root of the gravitational acceleration on Earth must equal to 2 pi times the radius of the satellite's orbit about the center of the moon divided by the radius of the moon times the square root of the gravitational acceleration on the moon, gm. So we can rearrange this equation and find the gravitational acceleration at the surface of the moon. And this is the ratio of the radius of the Earth to the radius of the moon squared times the radius of the orbit of the satellite on the moon over that on Earth, all cubed, times the gravitational acceleration on Earth, ge. And this can be written as re over rm all squared multiplied by the radii directly proportional to the mass. So the mass of the moon over the mass of the Earth times ge. So now we have an expression for the gravitational acceleration on the moon's surface. So we can actually calculate this by putting in our values from part B. So gm is equal to 6370 kilometers over 1737 kilometers squared times the ratio of the masses 0.01230 times GE, which is the gravitational acceleration on Earth's surface, which is 9.81 meters per square second. Hence, we get the gravitational acceleration on the moon's surface to be 1.62 meters per square second. So this gravitational acceleration is roughly 1/6 of the gravitational acceleration at the Earth's surface.